Lastly, what we're going to do is graph intersections and unions. So consider a coordinate grid and two inequalities graphed in the same coordinate grid. Let's say we have a line that passes through here, and we have another line that passes through here. When we graph two inequalities on the same coordinate grid, we divide the grid into four regions. We have a region here, we have a region here, we have a region here, and we have a region here. Unions and intersections consider all of these regions in order to create the solution set. An intersection is going to be any shaded region that overlaps two solution sets. For example, if I'm shading above one line, let me use a different highlighter color for that. If I'm shading above my red line, and I'm also shading above my blue line, then the intersection would be the region where they overlap, which is this red region right here. If I'm looking at a union, it would be all three areas combined. And so the solution would be the combined intersection of all three. Conversely, if I shade above the red line again, but below the blue line, the intersection is now this blue region that we have shaded here, and the union is all three regions together. So we're going to consider that while we go through and look at these intersections and unions. So let's start with graphing each of these. Now recall that AND represents an intersection. We want the region that satisfies both inequalities. So we're going to start by graphing x is greater than 1. Recall that x equals 1 is a vertical line. It's going to run through the x coordinate. Now, we don't have an above or below, but we can still use the same concept when we're thinking about the shaded region. X is greater than 1. We're going to shade to the right of the line. But don't go and shade the whole thing yet. Just make a little note about what area we're going to shade. Because we're looking for the overlap in our two shaded regions, so we don't want to have to shade an entire area and then erase it afterwards. Next, we'll go ahead and graph y is greater than or equal to 2x minus 1, starting at negative 1, and using our slope. Now, because y is greater than 2x, we're going to shade above the line. Now, what we want to do is we want to look for the overlap. Well, we can kind of see that if we're shading to the right here, and we're shading above here, that we have an overlap in this whole region. And that's where our solution set's going to be. Let me use the highlighter to help you visualize it. We're shading to the right of blue. That's our vertical line, x is greater than 1. Then we're shading above the line y is greater than 2x minus 1. So we can see how this darker region in the middle is where our solution set lies. Any point in that shaded region. So let me go ahead and get rid of our highlighting. And we can see that this purple region is where our solution sets lie. Now we want to check to make sure that our shading is correct. Therefore, pick a point that's inside the shaded region. We have the point 3, 8. If 3, 8 is indeed a solution, as well as any point in that shaded region, we should be able to substitute it into both of the inequalities, and it's going to be true for both of them. So we'll start with x is greater than 1. We have the ordered pair 3, 8. For x is greater than or equal to 1, well, 3 is indeed greater than or equal to 1. So the point is definitely true for our first ordered pair, or our first inequality. Let's check it with the second one. Same ordered pair. We're going to go ahead and substitute in 8 is greater than 2 times 3 minus 1. Is 8 greater than or equal to 5? Yes, it is. So it satisfies both inequalities. So we know that anything in that shaded region is going to be a solution to our intersection. Recall that OR represents a union. So a union, we want to combine all the solution sets. So in some ways, graphing unions will be a little bit easier because we don't have to think about where they overlap. We just want to take all of the shaded area. So let's start by graphing our first inequality. Starting at our y-intercept, we have a negative slope. And this is also a shaded line. Since y is greater than our line, we shade above. And since we're doing a union with OR, we can go ahead and just shade the whole thing. Next, let's go ahead and graph y is less than or equal to negative 2. That's a horizontal line at y equals negative 2. That's a really bad horizontal line. Let's try it again. There we go. And since y is less than, we want to go ahead and shade below. And so the union is the ordered pairs that satisfy either inequality. Anything in this shaded region on the right is going to satisfy our first inequality. Anything in this shaded region below is going to satisfy our second inequality. But anything outside this shaded region will not satisfy either inequality. So how we check to make sure that our shading is correct, we want to actually prove that these points are not a solution. We want to make sure that the point negative 8, 0, or any other point in this region is not a solution. Which means we should substitute it into both equations and make sure that we get a false statement. So is negative 8, 0 not a solution? Well, starting with the first inequality, y is greater than or equal to negative 2x minus 8. 0 is greater than or equal to negative 2 times negative 8 minus 8. Is 0 greater than or equal to 8? No, it's not. So far we're so good. Negative 8, 0 is not a solution. Let's check the other one. Y is less than or equal to negative 2. Is 0 less than or equal to negative 2? No, it's not. 0 is greater than negative 2. So again, we know that it is not a solution. So we know that our shading is probably correct because we did not get a solution when we plotted something outside of the shaded region.